Okay, so our last but not the least presenter is Sebastien DENNETIERE from RTE, French utility. He is going to talk about modeling and analysis of large DC grids with EMTP, new CIGRE benchmark with mixed VSC LLC technologies.
Thank you. So hello everybody. Just a few introduction and a few words on RT. This is a French TSO, and we're in charge of the operation maintenance of the transmission line, AC and also HVDC. We are roughly 20 people working in the area of 20-25 on EMT simulation, on offline and real time, and we are facing now more and more integration of HVDC on the grid, and this is why we have a team now dedicated to this type of analysis. Many of them work on a real project, but here this is not a real study. I mean, it's a study done with the software, but this is not a real design. This is a design, a DC grid design that is based on work in the CIGRE. So I will give you some context on the modeling activities in the CIGRE working groups, the description of the new test system, a new DC grid test system, and some details on the implementation we did so far in EMTP. So the DC grid modeling activities in the CIGRE working groups. The many working groups have been created in 2011 on DC grid in the CIGRE. So you have the list here. So on the grid code, on load flow and DC grid control in the mesh HVDC grid. Some of you have been involved, for instance, Dragon have been involved in some of the working groups here. But in the B457, we work the guide for development of model for HVDC grid, converter in HVDC grid. We worked on the development and implementation of first large DC grid for the CIGRE that was not called a benchmark at that time, more a test system. So it has been implemented in 2013 in different EMT tools. And all the details, all the data, equipment, but also control system protection have been documented in the final technical brochure you have here on the slide. So this done has been, was finished in 2014, and there was some discussion in the CIGRE in order to do more development, a new benchmark on DC grid. And this this activity was really pushed by the Chinese manufacturer and State Grid also. So to give you more details on the first DC grid test system, it was implemented in EMTP in 2014. Not only in EMTP, but as I told you, in different software, as in PSCAT, we work a lot with PSCAT to have exactly the same test system, same control, same data. We try to do our best to have something that is really documented in the technical brochure. It's available to all the EMTP users now. You can just ask, and you can download it. The test system that is described here. And all the details are in the technical brochure. So in this test system, you have this is only VSC technology, all the converter of VSC. The dotted lines are cables, plain line or overhead lines. You have, but all the AC grid and the offshore grid on the right side have been modeled in the EMT tools only with Thevenin equivalence or source and impedance, no real control on the AC side. So now the new DC grid benchmark, actually. So it's a part of the work done in the B472 working group. the structure, so this is the new design, the new test system. So it's bigger than the previous one. It has been proposed by State Grid Corporation of China. It is normally should include, and it is designed to include all realistic application coming in the next years, especially PV connection, wind farms, DC-DC converter, and it includes also, compared with the previous DC grid benchmark, it includes also LCC converter connected to the same grid and VSC. Here in this new test system, you have many more line cables here, so you can more easily use DC circuit breaker, for instance, to clear fault or to clear fault and recover from the fault. And in this working group, they decided not to do only one DC grid benchmark at this one, but to do 7 DC grid benchmark. This one is the most complete one. You have the other one, the B, so they are called BM for benchmark. BM1 to BM6 are smaller, and they are presently under development in the different software tools, so EMTP, PSCAD, Dixinant, RTDS. So not only EMT, because in the previous working groups it was only EMT simulation. Here it's also phasor domain tools. But the BM7, we had many discussions in the working group, but people did not want to model it in an EMT simulation tool because it was too big, and so we decided actually to try to do this in EMTP, and in order to show the constraint and the result, and if it works, to present the details. So what I will present you is the work that is in progress and the work that has been done so far. So the benchmark, right? The structure of the benchmark is composed of different parts. The first part is the BM4. BM4 is actually the DC grid that was the first DC grid test system that was done in 2014. So it's exactly the same. We just included some additional wind farm inside, but this is same structure, same data inside. Now you have BM3, that is another test system defined by this working group, including PV as well, BM1 with 5 converters, and the BM2 that is a mix between LCC. So on the, if I look here, on these 4 converters are LCC converter, and it's a 800 kilovolt system here, bipolar system. And so all this benchmark, all this test system are interconnected together in order to create the BM7 DC grid. So now we'll give you some more detail on the data we use for this test system. Most of the data come from the previous DC grid test system. So we have 60 pages of description of the data, control, and equipment in this brochure. So most of the data come from this technical brochure. So all the VSC converter or MMC converter, as with the topology you have here, actually it's written to 201 level for MMC converter, but that was in the previous DC grid. Now the number of level will depend on the voltage level you have, because you have different voltage level in the DC grid. You have monopole configuration and also bipole configuration in this DC grid as well, depending on the voltage level. Control system data, it's really classical, and there is no new development here compared with the previous DC grid system. So you have the classical upper level control that provide the voltage reference for each phase of the converter, and some low level control to suppress the circulating current, to do modulation and balance the capacitor voltage. So this is described also in the brochure and implemented in the test system. At the end, we have 22 converters in this test system, 13 converters in bipolar configuration, and 9 in monopolar configuration. So at the end, you have 26 plus 9, 35 individual converter units, actually, with MMC. So the table and the data here are small, but this is all the ratings and operation mode set point for all the converters, and especially all the VSC converter. So the VSC converters, some of them are in PVDC droop control, many of them actually. There is only one that is in VDC control, to similar such as a slack on the AC grid. And we have also many of them in VF control connected to wind farms. And different voltage level, of course, here. So AC-DC converter, you have the list of the different voltage level that are implemented in this DC grid. The wind farm as well, connected to AC-DC converter, and PV connection. So now the implementation of the DC grid model in EMTP. If for those who are familiar with the EMTP, you have different type of models for the converters. I'm not talking about control, but just the converter model, from model 1 to model 4. Model 1 is the most detailed model, with all the IGBT model in detail with their nonlinear characteristic. The model 2 is a representation, a simplification for which you have all the IGBT and diode that are represented by R on, R off resistor. These two models can be used to and connected to the full control of VSC converters. So that means that you can have the capacitor voltage balancing included in the control to connect to this detailed model. The model 3 is actually, it's an aggregated model for each half arm. So you can take into account the dynamics inside the converter, but you don't have, the assumption is that the voltage balancing is perfect inside one half arm with this type of model. What is really interesting with this model is obviously reduce the calculation times. It reduces not the network and the electrical nodes, because the previous one, there is a technique to reduce the electrical nodes, but it reduces the number of signal from the control system to the converters. So that reduces, of course, the calculation times at the end. And the model 4, that is an average value model of the of the converter. It's DC control current and AC control voltage on the AC side. And actually, this model is not really used for EMT simulation here, because you don't have the dynamics inside the converter, and it's not really a good model, especially when you do DC fault. So the one we use for this DC grid benchmark, as we have more than 30 converters at the end, is the model 3. At the beginning, we used the model 2 in order to have all the control inside and even the lower level control with the capacitor balancing, but it takes time and it's not really useful. We have many tests showing that and doing the comparison between both. And for this type of study, when we have so many converters, it's not really required. The model 3 is really good when you have really detailed model, when you do the design and dynamic performance test, for instance, with a manufacturer model. Now for the DC circuit breaker, it's the model that has been used. This is the hybrid DC circuit breaker model. The structure is this one. Actually, it's the one published and used by ABB. So you have an inductor in series with the power electronics equipment, the main DC, the DC circuit breaker, in order to limit the rate of rise of the DC current when you have a fault. And you have two branches. The first one, the top level, you have a fast disconnector and a DC breaker. So the normal path of the current is to go in the upper branch when you don't have any fault and when the DC breaker is closed. And when the DC breaker is operated, so you open it, the first thing is you operate the auxiliary DC breaker and the fast disconnector, so the current will go in the lower branch, and the different cells with the surge arrestor and the valve are open step by step, and the surge arrestor will insert a high value of resistance in order to decrease the fault currents inside the DC line here. So this model, actually this one is the detailed model that include all the valve, and the valve are modeled with an aggregated IGBT nonlinear model. So this is the internal part of each valve here. If you have here one valve, it is modeled with this one. And the value of the nonlinear characteristic here is based on the data we receive from the manufacturer, because outside this working group we have some collaboration with ABB, so we have some data available, and the characteristic has been modified in order to be realistic. And the same for the other valve that are here. And the surge arrestor characteristic are modified in order to take into account the voltage level. So for wind farm and PV, we didn't develop anything. We just used the model that are provided with the EMTP, especially for the doubly fed machine and the PV. Some of the PV park are connected in AC, so with an MMC converter to the DC grid here, and some of them we connected directly to the DC bus here. It's realistic or not, but there is different solution, different possibility to connect the PV to the AC or to the DC. So we did both in this benchmark. For the LCC bipolar system, we have 4 LCC converter in the grids. We use also the one provided in the MTP library, and we modified the main parameter in order to be consistent with the parameters and the voltage level, for instance, in this DC grid. So you have model for the rectifier side and model for the inverter side. The model of the high voltage equipment are the same. What is different, this is the control system and protection. So this is the full model in EMTP. All the DC, AC line and cables are modeled with the wideband line, wideband models, in order to have a correct modeling in the frequency domain for any transient that occur on the AC side or on the DC side. The DC-DC converter, we use ideal units so far, because that was more simple for us, and we can include more detailed models. But right now we had some, that was enough difficulties in building this model. And actually the problem and the difficulties are not to build the model itself, but it's to be able to run it and to have a stable and correct steady state, at least. And one of the challenges is to be even is to start the system, is to energize the system. And especially when you have VSC and LCC at the same bus bar, it's not so easy. And for the previous DC grid, there was only VSC, so the energization is, let's say, simple. You close the AC circuit breaker, you have obviously transient, but it's not so bad. But when we have the coupling between LCC and VSC at different point of connection, we have also protection inside the VSC. It's not so easy with the wind farm as well. So it's a lot of work, and again, we still have some work to do in order to have a correct steady state before starting to do some transient on the grid. But the simulation run, actually we have a pretty good result in steady state, not perfect, but we're still working on it. This is some figure on the system side and timings. So you have the number of electrical nodes, a little bit more than 3,000 on this grid, the number of wideband line cables, and obviously a lot of control system signals, because all the control system have been designed in the software. So you have all the control system open. You can have access to everything, all the details inside. This is not compiled code coming from Simulink. Usually we use it. We use Simulink and import the control system in Simulink. But here, as it is a design that is intended to be used by many different users, we prefer to build the control system and to make it available. So this is why you have a lot of control system signal inside. And the simulation timing. So this is some results here for a 4-second simulation with a 50 microsecond time step. You have roughly a little bit more than 30 minutes on my laptop, actually.
Which
so
is not bad.
Yeah. You mean my laptop or my?
For me, it will be maybe 5 minutes.
Yeah. So this is the result we got so far, and this is some example of a test we can do. This is a zoom here on one part of the system. This is one converter. You have here that is connected to different bus bar in DC. This system is a plus minus 400 kV system. You have the LCC that is at the top level here. And what we did is in one line, this is the internal circuit in this line. We added a DC circuit breaker, and we did a fault here, pole to ground, single phase permanent fault. And the DC circuit breaker open and remove and actually disconnect the line permanently. There is no reclosure here for this first test. And so this is some waveform we got so far. And this is a current here inside this DC circuit breaker. You have some, the time required to detect the fault. So we don't have any protection algorithm here implemented in the DC grid. It's just, we just send the order 5 milliseconds after the fault in order to simulate the time required to measure the fault, detect, and send the signal to clear the fault. So here, this is the different signal to send to the DC circuit breaker. You have the different branches here, and you see the decrease in the DC current in order to stop the DC and to clear the fault. You have here a different oscillation due to the fact that you use 2 sections and you have reflection inside between the DC circuit breaker. So this is some preliminary result we got. What is important is to show that the simulation of large DC grid is not limited to phasor domain tools. Actually, we had many discussions in the working group on this topic, and people didn't want to work with the MT tool, and they preferred to do it in phasor domain due to the simulation time. But actually, this is not the same type of accuracy and problems you can analyze with this with the phasor domain tool, especially when we are doing DC fault and even transient on the AC side. So the large grid has been implemented. There is still some work that has to be done in order to improve the system, and this is mainly parameters that have to be checked and tuned. The simulation timing are quite good for such a large system, and now the idea of this DC grid test system, not the one that has been implemented here in the EMTP, but in general, this is to test control protection innovative solution that can be implemented in this test system. So you can have it and implement new algorithm for protection first and new algorithm for control. This is, the idea is for us is to finalize this work within a few weeks and provide it to all the user in order to do simulation and test with it. So this is available for any user, CIGRE member or not. And we wait for your feedback. Thank you.
Excellent work, Sebastien. You're a patient man. Can you show us again slide 21, please? Okay, I didn't quite understand with the DC circuit breaker. As far as I know, UFD, ultra-fast disconnector, takes 2 milliseconds to open. So when you send the trip signal, the current keeps going for another 2 milliseconds and then drops. But in your case, I can see it drops down from 6 kiloampere instantaneously. I'm just not sure how detailed your model is.
Yeah, I have to check again if the, because they are synchronized or not. No. Yeah, you're talking about, just a second, about which part?
Yeah, that one.
Yeah. Which, okay. This one you're talking about?
No, the left, yes. That's mechanical switch, which takes at least 2 milliseconds.
Yeah.
So once you commutate the current from the auxiliary branch to the main branch conducts for another 2 milliseconds, just waiting for the contacts to get fully in the open state, and then you can open the main branch.
Yeah, actually, what has been implemented, it's really, we are still working on it, but actually the control system that are sent to each element here, the timing are very short, and probably we didn't use, because the timing you're talking about, you have to implement it. It's not the physical behavior that is modeled inside this circuit breaker.
It's sufficient.
It's a delay.
Just a delay.
Yeah, but that has not been implemented here.
Okay, well, we've done a lot of work in promotion project. Yeah. RT is a member, so maybe speak with Olivier and you can read the reports to improve it.
But actually, just to mention that this work and this implementation in the CIGRE DC, the test system, we probably have to improve it, but it was just to be able to see the system, if the system is stable after when the fault is removed, actually. Yeah. So for sure we can improve, not the equipment, not the model of the circuit breaker itself, but for instance the timings, for sure.
And the very last, just a quick comment on the DC-DC converters. Yeah. In B476, we have developed the first draft model for 2 different types of DC-DC converters. Okay. And I think SGI is quite involved, so very soon you should be able to get through SGI even. We did it in PSCAD, but SGI is working, I think, in EMTP. Okay. And then you will have a lot of more fun. Yeah, of course. Each DC-DC converter is too.
Of course. Because here it's an ideal transformer, and we didn't work on it so
two
far.
more VSCs for DC-DC. Enjoy it.
Yeah, and what is the time step you use? Is it a detail or an average value model?
It depends really which one you want to use.
You have both?
There is a direct conversion or based on dual active bridge.
Okay.
Dual active bridge is two VSC converters,
Okay.
front to front with a transformer.
Okay.
That's gonna bump up your 18,000 seconds. All right.
Good, thank you.
Just a fast question, Sebastien. I suppose you use artificial voltage source, ideal voltage source for accelerating initialization of valve?
Yeah, of course. We have, actually, there is many, if you can see here, where is it? Tricks, yeah. That are not hidden because there is some tricks here. You see that the DC-DC converter, there is some switches here.
Right.
In order to go step by step and energize step by step. They are not realistic, they are not real. But there is many tricks in order to, they are not hidden, they are here, but just to, because it's difficult to start it.
So yeah, we saw a result when you make your fault at 1.5 seconds.
Yeah.
So maybe that's take 1 second for.
Yeah, right now it takes 1.5 seconds, but I work with another colleague of mine, but I'm not happy of the steady state at 1.5 seconds. We still have some small oscillation that are not correct, and even if we wait for a longer time, so we have to check the control, the tuning, and things like that. Just.
And I
So,
suppose
the first test system, the BM4, the steady state was correct after 2 seconds. Obviously, there could be some solution to automatically initialize this system, but you need to initialize the control. You need to do a load flow in the DC part, load flow in AC part. That has been done, but there is nothing here that is automatic. So you have to play or to develop some script to do this automatic initialization.
It's a complete, it's a really complex question. Maybe with a parallel computation, this kind of benchmark will have a nice result in terms of performance concerning the speed or the.
It's possible.
Is easily be separated in 5 or 6 CPU.
It's possible.
Another question. What is it? How do you detect a fault on a DC grid? What's the algorithm? Do you know?
I think there is people more involved in this type of topic than me.
Okay, so in this case, you just open a switch.
Yeah. Here there is just a
Okay.
ship, but probably Dragon.
Yeah, that's a whole work package in promotion. You can use partially selective, fully selective, or non-selective strategy. Normally, you use a rate of change of voltage, a Rokov strategy. It's just local measurement, but there are disadvantages. So in simple terms, it's either Rokov or it's differential. So with differential, you need a pilot wire, and you have two signals on two lines of ends of the line, but it depends on the grid complexity and so on. So yeah, there's a lot of work still for this. Also for the control, just to build onto the same, you will need to coordinate. Do you have a dispatcher with a drone?
There is no dispatcher.
That's another.
But this is why what is important is to have the structure of the system that works. One point of steady state, and after that we can improve, and not us, but all the community can improve it.
It's a significant step.
Yeah,
so far,
this is the first step, but.
And so, did you ever had matching result with other software?
For this test, the test has only been developed in
And what
EMTP.
about with the smaller, like BM4?
Yeah, the BM4, which is the first test system we did many tests with PSCAD.
And the two software give same results, even in
Actually, we
transients?
spent something like 1 week in with the guy with the PSCAD just to compare. But we had some small differences depending on there is so many parameters. You have all the line cables, control system. we had actually, what we did is that first we did it in EMTP. We wrote the report with all the details, with all the control and the equipment, and they did it in PSCAD based on the report, not based on the EMTP. Just to, our idea is to have all the data available in the report and test the completeness of the data in the report. But again, it's a huge work to be sure that we have, even for a point-to-point link, actually.
Yeah, because the generic
there is
models,
so many differences in the model themselves. Yeah. If we compare PSCAD, for instance, in EMTP, the modeling of saturation, for instance, things like that are different. So it can be done. We do it a lot when we have a real project between manufacturer and us, and especially between PSCAD and EMTP, and we can have a very close result. But for this, it's a question of time. Mm-hmm. We need more than 1 week to do the comparison.
Thank you. No more questions? Thank you very much.